Hello, everyone. So welcome to the nice lecture. So this lecture, it's the content of this lecture, it's included in your first midterm. And so that's quite important. And it's also a very important lecture for your future homeworks and projects. So, and we are going to continue our discussion about abstraction to implement critical sections and synchronization between processes. And if you remember, last time we discussed that one of the main abstraction, which would make it easier to implement critical sections, exclusion from critical sections. So only one thread should be active in a critical section at a given time, or locks. And we discussed the implementation of locks using interrupts. And then we said there are some disadvantages of using interrupts and some dangers. And then we discussed about then using atomic operation, which are more sophisticated than load and store, to implement these locks. And one of them, it will be like test and set. If you remember the test and set, it takes a value and maintains a local variable. Think about test and set, maintains a local variable. And the atomic operation is that taking a value, updating the local variable with a new value, and then returning the previous value of the local variable. That's pretty much it. And this is an implementation, again, we discussed last time, of a lock acquire and lock release, and using test and set. And basically we use test and set here also to implement mutual exclusion of operating of the value is the value of the lock. Okay, so the lock value of the lock, which whether it is busy or free, determine whether you can enter or not in the critical section of the program of the user. And now we have a second, we use test and set for a second smaller critical section, which is only concerned of updating the lock value to busy or free. Okay. And if you remember, all these synchronization primitives involves wait. And the reason for that is because it's fundamental, because if you have two threads which wants to enter in the same critical section, you can only allow one thread to enter in the critical section, and therefore the other thread has nothing else to do but wait for the first thread to finish. Okay, so that's why waiting is fundamental. Okay, and the other thing, if you remember, if you wait, one way to wait, and it's easy to implement, is to do busy waiting. You constantly check whether the critical section is free, whether you can acquire the lock. But of course, this consumes the CPU cycles without doing any useful work. So therefore, waiting, what you want to, the best way to implement waiting, and the preferred way, is to go to sleep. So to put the thread on the waiting queue, and then to be woken up when the previous thread exits the critical section. Okay, so this is what you see here. If the value is busy, so if someone acquires a lock and has acquired the lock, it's in the critical section, you put the thread on the wait queue, and then you go to sleep, and then you reset this guard, which is again this guard. It's about, it's basically you freeze a lock for the critical section, which is concerned with updating the busy value. Okay. okay? And well, else it's the value is busy. You set the value to busy, so acquire the lock, and then you again set guard to 0. So therefore, you are going to allow another thread to look and to read the value, the lock value, and modify it. Okay. Any questions here? Okay. So note again that we have the same discussion. We had the same discussion like in the case of when using interrupt to implement acquire and release, and that is when we are going to set the guard to 0. There is when you are going to disable the interrupts, and this needs to be done. You cannot do before sleep. You cannot do before the thread on wait queue. Just remember. Why is that? You can look at the last lecture. So you need to do in some sense after, but then after the thread itself, which call acquire, cannot do it because it's sleeping. Okay, so that has to be done either by the operating system or by the next thread, which is going to be scheduled to reset the guard. Okay. So and here it's a simple example. Oh gosh. It's this is a great question. So one question here is whether the guard and value will be on the heap. Yes, they are going to be on. They are going to be global variables. So yeah, so everyone can access them. Okay, so now we've seen two implementations actually of acquire and release locks. And one is using interrupts and the other one using test and set. And this basically is to show you that actually the logic is very, very similar. And you can think about while test and set, it's similar with disable interrupts, and enabling and guard resetting guard to 0 is like enabling interrupts. Okay. And this is again the code for we went over last lecture about implementing acquire and release by disabling and enabling the interrupts. Okay. And if you remember also what we did last time, when we talk about locks, we did in 2 stages. First of all, we said we gave this very trivial implementation of the locks. Acquire, you disable the interrupts. Why you disable the interrupts? Because you don't want new threads to interrupt you, right? While you are in the critical section, right? And then the release is enabling the interrupts. But of course, this was very dangerous because if you call at the user level, acquire and disable interrupts, and you have a very long critical section, or you make a mistakes and you have an infinite while loop in the critical section, then your computer will hang. Okay, you can't do anything about it. The only thing probably is power off, power on, right? So therefore, is a more sophisticated implementation was to use disable and enable interrupts only for updating the value of the lock. So now you have a value of the lock, which is set to 0, and use disable and enable interrupts to update that value, right? Or to read that value. Okay. So now, yes, you still use disable and enable interrupts, but now it's very short. The critical section is very short and is going to finish very fast, right? So, and if you look again, if you look now at the same example, but now implementing acquire and release using test and set, we went again through 2 iterations. The first iteration was very simple, that while test and set value, so you are going, the value is a lock value. So while the value, this is while the value is 1, right? Again, the test and set here, if value is 1, it's going to return the previous value of the internal variable of test and set, and then set that variable to the new value, right? So if it's the previous one was 0, return 0, means that the lock is acquired, but now it's set to 1. So next time when someone tries, the value is 1, the internal variable is 1, so the internal variables will not change, and the test and set returns 1, so you are going to be stuck in the while loop. Okay, but it's again, the problem with this one, and the release is simple, you set the value to 0. But the problem with this one, remember, is this while loop, it's again, it's like it's busy waiting, which we discussed that we want to wait. We want to, sorry, it's busy waiting, which you remember we want to avoid, right? So again, in this case, we went to the second iteration, which we just also presented again earlier in the lecture, today's lecture, and you use the test and set only to protect the critical sections which are concerned with updating the value of the lock. And now again, this is much shorter critical section, so the test and set will be, you wait only for a very short time. And now instead of, like in this case, you are waiting, in the previous case, you are waiting as long as someone is in the critical section, do busy waiting, so consume the CPU cycles. In this case, in the more refined iteration, you are going to put the thread which is waiting on the wait queue, right? So there is no busy waiting. Okay. Any questions here? Okay. So, so where we are going again with synchronization. So let's see what we've done. We look at on the hardware support, low stores, disable interrupts, test and set, and compare and swap. These are similar, test and set and compare and swap. They are much more useful than load and store. And we saw how you can use this to implement locks. And also we discussed the abstraction about semaphores. And yeah, and then next also later we are going to talk about monitors. And it's again, the higher level, the abstraction, the easier will be for the programs, for the application to implement mutual exclusion and critical sections. Right. And so next we are going to go and talk more about this abstraction. Let's talk again about semaphores then, right? And if you remember, just to remind you, the semaphores, they are a little bit more sophisticated than locks. A lock can have only two values, 0 or 1, or busy and free. With semaphores, it's like a counter, right? A special counter, right? It's like you have a primitive which increments the semaphore and a primitive which decrements the semaphore. And if the semaphore is 0, then you are going to wait, right? You are very much you are waiting for a lock which is busy. Okay, so if you remember, so that provides you a little bit more a little bit more power, and therefore it also gives you more gives you more functionality. You can implement with a semaphore both critical sections, but you also implement a mutual exclusion, but you also implement scheduling constraints, basically signaling a process from another process, or a thread from another thread. And if you remember the example we gave last time about this was about, if you remember, it was about implementing the thread join, waiting the thread who launches create another thread, waiting for the creative thread to finish. Okay, it's again. So now we are going to move from locks and semaphores to a new abstraction, which is called monitors. And monitors are better, are simply more powerful. And the main idea is to split between and supporting explicitly these two functionality about mutual exclusion and scheduling constraints. And you use locks for mutual exclusion and what are called condition variable for scheduling constraints, right? So a monitor, it's a lock, and a 0 or more conditional variable for managing concurrent access to shared data. Okay, and we'll talk more about that. Some languages provide this natively, and most of the others you can use lock and conditional variables as a distinct abstractions. So I'm going again. If you have any questions, let me know. This is again. So these lectures, the past lecture and these lectures, are not very easy to follow because they are about concurrency, are about programs which execute concurrently. And like we discussed last time, you know, we as humans are not very used about handling many things which happen at the same time. We are much better in sequentializing things. So it's perfectly fine, if if you feel this is a little bit more challenging. But at the same time, this also means that you should spend a little bit more time to try to understand deeply what's happening here. Okay. Okay, so again, some languages provide monitors, and let's see what is conditional variables. So conditional variables, what is a conditional variable? It's a queue of threads waiting for something inside a critical section to happen. Okay. So, and the nice thing about the critical section and the conditional, nice thing about the monitors and condition variables is conditional variables allow sleeping inside the critical section by atomically releasing the lock at a time we go to sleep. Okay, so what I mean by that, here is what I mean. Okay, remember about this slide? I'll go soon, in presentation mode. Here, it's again, if you try to acquire the lock and the lock is busy, so the value is 1, you have to go to sleep. And what we want this to, we want this to happen is to put the thread in the waiting queue. But when you put the thread of the waiting queue, you need also to reset the guard, right? To let other threads enter the critical section to look at the value and maybe to modify the value, right? So now the sleep and the guard have to happen at the same time, okay? So they need to be atomic. And well, monitors provide, and conditional variables from monitors provide you this atomicity between the threads going to sleep and giving up, releasing the lock, because guard is equal to 0, release a lock associated with a guard atomically. You don't need to worry about that. That's what conditional variables in monitors are going to do for you. And that's why they are very useful. Okay. And here are the operations. The operation, you wait for the lock, okay, which you can atomically, this is going to, the operation is going to atomically release the lock and go to sleep. And you can require the lock later. We'll have a few examples to make it, to make it more understandable. And then you have signals. You remember that one of the use of the semaphores was to signal when a thread, an event, right, between two threads, right? So now you have a primitive which is called, makes a lot of sense. The name is signal. And you have also something which is called broadcast. So the signal is waking a thread which is waiting for some particular event to happen. Broadcast is waking multiple waiters, all the waiters which wait for that event. Signal, if there are multiple waiters, it's going to wake only one, and that's non-deterministic. You don't know which one is going to be waken up, and in many cases you don't care. Broadcast wakes all of them. Okay. Now, when you do that, operation of the condition variables, of course you need to own the lock, right? Because this is in critical section. This is one way to represent it, the monitors. So X and Y are conditional variables. Each of them is associated a Q. And yeah, and you have a lock which provides a mutual exclusion to the shared data in this monitor. The conditional variables are shared data, right? Okay. But it's again, one of the main advantage, you are allowed to wait in the critical section, and this is not allowed for semaphores, which makes the semaphores very much harder to use. So now it's again, let's see, and we are going to have a lot of examples, so we give you a better sense about how these monitors, how you use the monitors, and also we are going to talk about how they are implemented. Okay, so hopefully by the end of these lectures, you are going to have a pretty good feeling about monitors. Okay, so here it's an infinite queue, synchronized queue. You have producer, consumer. It's infinite in the sense that the producer can put any numbers of items in the queue, right? The queue is infinite, right? So how do you do this? The producer is like you acquire the lock, you release the lock, you have a buffer lock, and the consumer also acquires a lock and release a lock, right? And this is in order to protect the critical sections which are operating on the queue, right? You don't want a producer and the consumer to operate on the queue at the same time, because adding a new element to the queue and removing an element from the queue are not atomic operations, and therefore bad things can happen while both of them are manipulating the pointers, right? To insert or remove an element from the queue. Okay. And now you can use these condition variables like buff, CV, in order to signal the producer. That's basically what it says. The buff CV is a signal, is a way for the producer to signal the consumer that there are elements in the buffer, in the queue, right? So this is what it is. You signal it, and then what you do from in the consumer while it's empty. So you look for the queue whether it's empty, right? It's in the critical section, so it's fair to look at the queue because no one else will modify the queue while you are in the critical section to operate on the queue. And then you call this condition wait. So you're waiting for this signal for buff CV. And you see, this is the first argument of condition wait. And the second argument is buff lock. Why is that? Because if the queue is empty, right, this is true. So this in condition wait, and what you are going to do is basically you are going to put the thread to sleep, and you need to release a lock, right? This basically tells the condition wait to release the lock once the thread is put to sleep. Remember, we want here to have atomic operation, the sleep and releasing the buffer should be an atomic operation. Aaron, it has a question here. If you use a broadcast, it will create a race condition. Not necessary. We'll see that in an example, right? Because still, not all, you can wake up all the waiters, but only if all the waiters want to go to the same critical section, still only one will succeed. Okay. And the other one will go back to wait. So it's still going to, you are still going to be okay. Okay, so, oh, sorry, okay. Okay, so this is basically what happened here. So now, and I think this was a question last time. I don't, remember who asked that question. It was a great question about what you remember if you go to, I think it was in the context of test on set, why do you use while and not if? It's a similar thing here, and we'll explain why and what is the difference. And the problem here is that, if you look at this piece of code, will you just, the consumer, wait for the queue to be non-empty, to have elements in order to dequeue a new element from the queue, it has a while, right? And the natural question you can ask, look, why while? Because the thread is going to sleep, right? So why do you do that? And it's true that it's a good question. Let me start with that, right? Okay. You see that why should I do the while? Because it's like the thread is going to sleep and it's going to be woken up if another thread exceeds the critical section, right? So why should test again? And the answer here is that it depends on the implementation. Okay. You can actually, depending on the implementation, you can replace while with if, and that will be correct. Okay. So, and there are two implementations. One in which you need to put while, you have to have while, and the other one you need to have, you can use if. The first one, which requires you to have while, is called Mesa style, right? And because it was implemented in Xerox Spark Mesa operating system. And this is what most operating systems are using. The one in which you can use if is Hoare style implementation. This is a British logician, Tony Hoare. And in this case, you can use if, okay? So let's see how Hoare monitors. So this is the one you can use if, how they are implemented. So here is how it's implemented. You have acquire on both sides, and let's say the first in both cases, you protect the critical sections by a buff lock, and the code on the left hand side is going to send a signal, and as a result of the signal, the thread which are waiting on this conditional variable buff CV is going to wake up, right? So the thread on the left is going to send a signal, and the code on the right is going to be of a thread which is going to be woken up by this signal. Okay, so let's see what happens. So it's what happens when you execute this signal, you automatically release a lock, the buff lock here, and the CPU, and you schedule immediately the thread which is waiting for on the buff CV conditional variable. You are going to execute it, and then at the end, you are going to release the lock, and then you go back and continue to execute the first thread, which signaled the second one, right? And that's what it is, right? So this is the implementation. Now, so this seems like good, right? It's basically, again, the signal. When I signal someone, I stop, I give the lock to the thread which is waiting, and the operating system will schedule that thread to execute, exit the critical section, and after that I get the control back. Okay, this is correct. What is the problem? The problem here is it's a little bit harder to implement and may lead to a lot of context switches. Furthermore, as you'll see from the next Mesa style implementation, it's not really necessary. And here it's about Mesa implementation. With a Mesa implementation, when you after you signal, you do not give the control to the thread waiting for a condition variable. Instead, what you do, you just take that thread waiting on the conditional variable, and you put it, move it from the waiting queue to the ready queue. It's ready to execute. And then you continue. Okay. And eventually later when you are done, you are going to schedule, the operating system is going to schedule the thread, which is now on the ready queue. Okay. Sometimes later. But you see now, so what is, but we see now that now you need to check this condition again, is empty queue. Why? Because in the meantime, there can be another between, in the meantime, you can have a race condition and another thread comes and wants to acquire the lock because it's free. And now you are going to have two threads on this, which are on the ready queue, which want to enter the same critical section. So that is not good, right? So that's kind of the problem, right? Right, that's what. But by doing so, you are going to have less context switches, right? In this case, right, you have the first thread finishes, exits the critical section, then you are going to, after that, you are going to execute the second thread. So it's one context switch. In the previous case, you have one context switch going from the signaling thread to the thread which is waiting and back. So at least you have two, right? Okay, any questions? So let's look now at our buffer queue example and use a more and now we are using two condition variables for producer and the consumer. Let me give you the code. And we are also looking now is bounded buffer. So in previous case, we use only one condition variable and it was unbounded buffer, infinite buffer size. Here is bounded. Okay, so how you do, you have two variables. You can check whether the buffer is full or empty. And then if the buffer is full, while the buffer is full, obviously the producer waits. Otherwise, you enqueue an item in the buffer and you signal the consumer, because now the buffer is no longer empty and the consumer can take that element from the buffer. Okay, and the consumer the same. If the buffer was, it's empty, you can't do anything. There is no item you can take from the buffer. Okay, if the buffer is not empty, you dequeue it and you signal a producer that there is at least one free slot in the buffer you can insert a new item. Right? So this is how this is working. Okay. Any questions? So you see that fundamentally what you do is condition variable here is like we mentioned earlier, is to signal between threads when an event occurs. In this particular case, the producer signal to consumer when it's inserted an element in the buffer, and the consumer signals to the producer when it removed an element from the buffer, right? So now the producer knows that for sure it can add a new element to the buffer, right? Also, again, I want to reiterate that the thread, when it's waiting, it doesn't do busy waiting, it's sleeping, right? The condition variable, the semantics there, or cond wait, is to take that thread, put it on the wait queue, and release the lock to the critical section, buff lock. Okay, can you construct monitors from semaphores? The locking aspect, it's easy, right? Remember, you can use a semaphore which has only two values, and the wait, it's basically decrementing the semaphore. If it's 1, you initialize the semaphore to 1. If it's 1, you acquire the lock, and it's 0. If someone else thread comes and want to decrement it, then it cannot, and it has to wait, right? Because you need to wait for the someone else to increase, to increment the semaphore back to 1, right? This will be the signal, right? So you see things. But the biggest problem here is that the wait, if you do that while you are in a critical section, and you have to do that to be in the critical section, then you are going to wait and you are not going to release a lock, right? So that's the key. The monitors on the condition variable condition wait, that function is releasing the lock atomically when you go to sleep, right? And are this working? This is, what about this one, right? You release a lock, you release a lock immediately, right? You after wait, right? This will not work. And one of the reasons the conditional variables have no history, in the sense that I always signal, if I signal you 5 times, you are going to be woken only once, right? But semaphores have history. Let me see. Question. Yes, so this is exactly what I was saying. It's a great question, Taiwo. So the question is, it is half full. If the buffer is half full, will the condition variable still going to signal in the either case? Absolutely. That's exactly what we mean here. The condition variable has no history. Yes, you are going to be signaled. And in that case, the signal doesn't mean anything, because you may not, if you signal and there is no thread on waiting, then nothing will happen. Very good question. Right. And yes, this is exactly what I said. If the thread signals and no one is waiting, there is no operation. There is no op. If a thread later waits, then it's a problem right now here, because it's, again, if that happens, then it's going to, you wait with a lock, and the other thread cannot increment the semaphore which correspond to the lock. So you are going to be stuck. Okay. Anyway, so there are a bunch of questions here, and I invite you to answer the questions. I just want to, as an exercise for you, and you may be very well get some problem like this one and asking you these questions. But instead, because we are, running a little bit out of time, I want to go to the next part of the lecture, which is extremely important part of the lecture. And this is about reader and writer problem. Okay, let me just see. Okay, let me just add, I think I don't have the announcement before going there. Let me do verbally, and I'm going to add the slide about the announcement to the lecture right after, to the lecture slide right after the lecture. So basically, the most important thing is that obviously next week we are going to have the first meter, and it will be between 7 and 9 on Wednesday. Okay, and we are going to have also a session for between 7 and 9 p.m. on Monday for the midterm. So you can come and ask any questions you have. And, you know, this is pretty much it. We are going to provide more information as we go close to the midterm. But if you have now any questions, let me know. Okay. So now this is a more complex problem, and this will illustrate very clearly the use of monitors. Okay, so here is a problem. The problem is about accessing a database, which is shared by multiple people. So you have can have a bunch of people who want to write, and a bunch of people who want to read to the database. And these writes and read operations happen concurrently. And they modify the same data, right? So how you are going to implement it? One thing is to use a lock for the entire database, right? You read or write, acquire the lock, you do your job, and release the lock. So is that sufficient? That's a question for you. Yes, it is sufficient, meaning that it's correct, but it can be very slow, right? I mean, if you think about fundamentally, give me 2 examples why this is inefficient. It's exactly, Aaron. Aaron gave a great answer. So basically, for instance, if people only read from the database, there is no need to lock it because nothing will change. Okay. Also, there are other reasons we are going to discuss later, but even if you have rights, then the rights can be different records. They don't need to wait after each other. We are not going to solve this problem here. We are going to solve the first problem on multiple readers. We should allow them to read the database if there are no writers. Writers, yeah. Okay. Very good. So let's see what you want from the solution. Readers can access database when there are no writers. This is exactly like we said. If there are no writers, no value will change. So therefore, the readers, any number of readers can read concurrently. Writers can access database. A writer can access a database when there is no reader reading and no other writer modifying the database. And finally, we have some state variables. And we want only one thread to modify them at a given time. Right? This is the basic solution, the structure. For the reader, you wait until there are no writers, access the database, check out, and wake up waiting writers. And the writer wait until there are no active readers or writers, access database, and then you check out and you wake up other waiting readers or writers, right? So let me ask you this question. You see here, there is some asymmetry, and some asymmetry is derived from our constraints, right? If a reader, it doesn't need to wait until there are no other readers because it doesn't conflict with other readers. It can only conflict with writers. So that's why you wait until no writers. The writers is going to conflict both with the readers and writers, because if a reader is going to read the data while the writer changing the data, the reader can read garbage. But then there is another asymmetry. When a writer is done, is going to wake up readers and writers, while when the reader is done, it's only try to wake up writers. Why this asymmetry? Why do you think? Why do you think the reader is not just waking up the readers? Very good. The readers are all concurrent, so there should be no any other reader to wake up. Very good. Okay. So let's move on. So how do we implement this with our monitor, the beautiful abstraction we just learned about? All right. So you see, wake up a waiting writer and wake up waiting readers or writers. What are these? You can implement them condition variables. It's like signals and waiting. That condition variable. Okay. So we have two condition variables, okay to read, okay to write. And then what are the state variables? Well, the number of active readers, number of active writers. How many active writers can have at a given time? One, right? Remember, we cannot have two writers at the same time. Then you have the number of waiting readers are the readers which are waiting to read, and the number of waiting writers. When do we have readers waiting? Yes, when there is one active writer. Very good. So let's try the code for the reader. So here it will now look like acquire lock, release lock. Because within this code manipulates the state variables. Okay. This is a reader. So I'm looking if there are no active writers or waiting writers, right? So if there are either active writers and waiting writers, then you wait. You increment the number of waiting readers, because now is myself, I'm going to wait. And then I'm going to wait on the condition variables, okay to read. Need to wait until it's okay for me to read. And release a lock. Okay. Now, why I'm doing here, I am waiting for both active writers is normal, right? I cannot read on someone who's writing. But why I am waiting also for waiting writers? Because this means that I'm going to wait for other writers to write before me, before I can read. Why is that? Why do you think is that? So a few people say, we don't read garbage or we don't read wrong results. But why is that? Because why would do that, right? Because in that case, you can have, so here is what can happen. You have a bunch of readers, no writers in the system. And now I have a writer which wants to write. And that writer has to wait for the current readers to complete. And in the meantime, I have another reader which wants to read. And I'm not going to let this reader read the database together with the other readers before the writer is scheduled to write and update the database. Okay. So it won't result in wrong results, right? What the reason you do this, right? So, but it is fundamentally what this gives. It gives priority to the waiting writers, right? That's what happens, right? And why do you give priority to the waiting writers? Is the reason was, the answer is correct, is from Akshay, is that you want to read the most up-to-date information. Otherwise, you can starve writers. If you always have readers coming in, you will never update the database, right? Before a reader terminates, finishes, you have another reader. So you're going to schedule that reader and so forth, right? So the writer will not be able to be scheduled. Okay, sounds good. So anyway, after, if there is no active writers or waiting writers, then you are going to increment the number of active readers, because now you are allowed to read, so you are active reader. And you release a lock. You access the database. It's read only, right? And then after you are done, you acquire the lock and to manipulate the state variables, and you decrement the active readers, because I'm done. And now what do I need to do? Well, what I need to do is to wake up threads which may wait, for instance, to write to the database. So here, if active readers is 0 and there are waiting writers, then I'm going to send a signal, okay, to write. Okay. Simon has a great question here. What if new writers are coming all the time? When do you get to read if you keep waiting for all writers to finish? That's correct. Okay. So in this particular case, Yeah, if writers come up all the time, you are not going to get a chance to read. In practice, you need to be a little bit more sophisticated. But that's a good point. So this is one question here is why you release locks there? Why don't you release a lock all the way to the end? Why is not access database part of the critical section here? Yes, so any readers can get the lock. Right? You don't change the state variables. The locks are for changing the state variables. And in this particular case, you also want all the readers, if there are only active readers in the system, if there are only readers in the system, you want them to read concurrently. Right? Very good answers. Now let's see the code for the writer. It's very similar, right? You acquire the lock, and now you check whether you can write. And what is the test there? There should be no active readers. You cannot write while you have readers reading the data, manipulating the state variables. And obviously, you cannot have writers, active writers. You don't, if you have any of those, you go to wait, and you wait on the conditional variable, okay, to write, because you are a writer. If not, you are going to increment active writers, because now you are an active writer. Release a lock. You access the database, read, write. And then once you are done, you acquire the lock again to manipulate the state variables. You decrement the number of active writers because now you are no longer writing. And then you check if the number of, if there are still waiting writers, you are going to wake up one of those by sending signal. And now if that's not the case and the number of waiting writers is 0, but there are waiting readers, then you send a broadcast okay to read. So now you see the use of the broadcast now. You are going to wake up all the readers because all the readers can read at the same time, concurrently. Okay. Okay, let me answer this question. The question is, does there exist some situation that a reader is waiting to read some intermediate state while some writer joins to wait? Yes, definitely. Yeah, but the writer is not going to be able to modify that state. So we are going to be fine. Oh, sorry. So basically you say if a reader, yeah, so the reader is already waiting. And now, yes, a new writer joins to wait. Yeah, so that's valid. And in that particular case, the writer will be prioritized over the reader. But it's again, at a given time, only one reader and only one writer can manipulate the state variables. So it should be fine. Okay. We discussed why giving the priority to writers earlier on. Okay. So now let's do the following. We are going to, in order to get hopefully you to better understand what's happening here, let's go through a simulation. Okay, so let's assume the following sequence of operations. We have three writers and one writer, three readers, R1, R2, and R3, and one writer. Okay. So first we get the first reader, the second reader, then the writer, and then the third reader. Initially, all the state variables are set to 0. So let's see what happens. R1 comes along. There are no waiting threads. There are no other threads in the system. So let's see what happens. It acquires a lock, check whether there is an active writer or a waiting writer. Both of these variables are 0. None of such threads in the system. So you exit the while loop, and R1 can start reading. You increment the active reader variable. You release a lock. Okay, we know that why. You access the database. And let's say that while you are accessing the database, R2 comes along. Okay. Remember, now the number of active readers, it's 1, because R1 is still accessing the database. So what is R2 doing? Obviously, it's going to execute the same code. It's acquiring the lock. Now it's checking whether it's an active writer or a waiting writer. None such thread is in the system. So again, you skip the while loop and you increment the number of active writers. Release a lock and you access the database. So now both R1 and R2 are accessing the database. The number of active writers is 2. All the other state variables are 0. Okay. So now it's again, assume the readers take a while to access database. And and assume that during this time, now when the writer comes along, W1. So what is that? The writer is going to execute the writer code. So it acquires a lock, and now it looks at active writers and active readers in the system. There are 2 active readers, no active writers. Still, because there are 2 active readers, the writer cannot proceed. So what you do? You increment the number of waiting writers, right? Because now you have to wait. And you wait on OK to write condition variable, and you release a lock. Right? So W1 cannot start because of readers. Finally, R3 comes along, acquires a lock, and now it checks whether there are active writers or waiting writers. There are no active writers, but there is 1 waiting writers, W1. So therefore, the new reader, R3, has to wait. So you increment waiting readers now by 1, and you are going to wait for the condition variable OK to read, and you release a lock. Okay. Any questions here? Is that clear so far? Okay, so let's go with our simulation. So status resist time, R1 and R2 are still reading, W and R3 are waiting. Okay. So let's say R2 finishes. Right. R1 still accessing database, W1 and R3 are still waiting. So R2 is going to acquire the lock to update the state variables, in particular to update the number of active readers. Now it's less to decrement it because R2 finishes. And now it's looking whether the active, whether it can wake up any thread. And he's looking whether there are active readers, if there are no active readers, and there are waiting writers. Okay. So he's looking for that. And then the condition is false because there are still active readers. This is R1. So then you release the lock. And R1 now is done. Okay. Now let's say R1 finishes. Sorry, R2 is done. Right? Now say R1 finishes. He's doing the same thing. Acquires the lock, decrements the number of active readers. Now both R1 and R2 are going to be done. And now active readers become 0. And are there waiting writers? Yes, there is W1. So now this condition is true. And now you are going to signal to the writer that it's okay to write. Okay. So all right, readers are done. You can see the signal to writer W1. So now the writer, which was waiting on the condition variable okay to write, receives a signal. It's moved to the ready queue, and now we can start executing this thread. It acquires the lock back because remember, we are still in the critical section. Decrement number of waiting writers. I am no longer waiting now. Increment the number of active writers. I am active now. Release a lock and access the database. And this again, although I am writing now, it's still okay to access the database outside the locks, because this database is going to be accessed. You can show only if the number of active writers is 1. You are guaranteed that it will not be greater than 1. Then say you are done. You acquire the lock. You decrement the number of active writers. And now you look to signal. Again, you give priority to the waiting writers, right? Because you want to prioritize writings over readings. So if there are waiting writers, you'll call OK to write, but in this case, there are no longer waiting writers. So therefore, you are going to look where there are waiting readers. And yes, there is one. It's R3. So then you are going to signal to R3 that it's okay to continue to read. And now I start executing the code for R3, who is resuming the execution, acquire the lock back, decrement the waiting readers, access the database, acquires a lock, decrements the number of active readers, release a lock. So we are done. So now all the readers are done, all the writers are done. Okay. So here is a question, Haoyan, from Haoyan. If we want to signal the writer with a fixed order, how should we modify our code? Any suggestion here? So the question, if the way I understand it, if we want to signal the writers in a particular order, how do we signal them? Any suggestion here from the class? Yes, that's great. You know, yeah, there are two ways to do it. One easy way, you can use a different condition variable for each writer. Very good, Taiwo. The other one is to have more condition variables and to have a queue of writers, right, to maintain it, and only wake up the one from the head of the queue. But it's pretty complicated. But anyway, it's a possibility. Very good. Okay, so we are all done. So here are some questions. Let's see, let's check your understanding. So let's say, you know, sorry. Can readers starve? Yeah, you we answered this question. Readers can starve if you have continuous stream of writers. Here is the second question. What if we erase a condition check in reader exit? This one. So basically we say wherever a reader finishes, say it's okay to write. What will happen? Is this a good idea? Is this going to work? Any drawbacks? Okay, one question here, one answer here is writers can start writing when readers are still reading. Others can be reading. Okay, let's look. Let's look at this one. In order to answer that question, let's look at the code. Okay to write. So this is a writer code. Here. Okay. So what will happen here, guys? You see, you get okay to write. You go out here, it's waiting right to you decrement waiting writers. But then what do you do next? You go back to the while loop. And in the while loop, if there are still active writers or active readers, you still cannot write. You go to sleep again. You see? Because this while, because you check again this state variables, you are going to be fine. What this will happen is that It just wakes a writer, just for the writer to go immediately back to sleep. So you just gratuitous context switching. So it's an efficiency problem. It's not a correctness problem. Okay? Good. Let's go to the next one. Let's go. Further, what if we turn the signal into broadcast? Okay, okay, instead of having a condition broadcast, okay, to write. You broadcast okay to write to everyone instead of the signal. What will happen in this case? Is it correct? First question. Okay, let's try to give an answer. Anyone? Yes. It's actually it's correct, Sonali. Yeah. Yes, and it's absolutely correct. It's for the same reasons. You see, the fundamental observation here, let me just, it's again. The fundamental observation here, it's again for the writer. I'm going here to the code. You are still in the while loop. So no matter, even if you are going to be woken up by mistake, no matter who is waking you up, you are still going to check whether there are active writers and active readers. And if they are, you go back to sleep. So it's an efficiency problem again. It doesn't matter how many times you are woken up. You are not going to do stupid things. Okay. And the last one, finally, if we use only one condition variable, call it okay continue instead of two separate ones, both readers and writers are going to wake up. These are going to be correct. Yes, it's going to be correct for the same reason. Neither writer nor the reader are going to continue if the test for the while loop is still true. Okay. So here is what happens. Right, and this is what I'm going to end up with this one. Okay. So you can use one, right? Okay. Although there is, in theory, there is one thing here, right? And this is subtle things. This is correct with one condition, okay, to continue, right? It's actually, if I, okay, continue, is going to wake up one single thread, and that single thread is the incorrect one, and go to sleep. So here is the thing. If I wake up, if I have only one okay continue conditional variable, both the writers and the readers are going to wake up on that. And now assume that by mistake, not by mistake, it just happens. I wake up the reader. The reader is going to check, and there are waiting writers, and it's going to go immediately to sleep. But now these signals were spent out. Okay. And the writer cannot continue. It's already, it's asleep. The reader is asleep. And if there is no other thread coming in, we are deadlocked. In order for this to work, we need to also change this signal from the write reader to broadcast. Okay. Okay, so you need to broadcast. Okay. and you also need to broadcast. So you need to do some changes. So the summary here, and we are going to end up with this, is that these while loops are extremely powerful, right? Because they are going to guard against doing stupid things or incorrect things if you are woken up by mistake. So we are safe. So what we need to be careful about is that because there is no history with these condition variables, I am protected to waking up the wrong thread. But then if I am waking up the wrong thread, that signal was wasted. And the correct thread will not be woken up. So you can have deadlocks. So that's why here you need to be careful. What you need to be careful about. That's why you have to be liberal with the broadcast. So we are going to end up with this one. And I think that it's a good place. We are done with this example. Please take a look at these examples carefully, and for the exam. And I'll stop here, and the lecture is done. There is one last question I'm going to try to answer. And thank you. And I'll see you on Tuesday and Monday. And thank you. So 2 questions. One question, the while loop give us good protection, but doesn't that cost a lot of CPU cycles since we are constantly pulling? Absolutely. It's inefficiency. You are absolutely correct. It's inefficient. It's correct, but inefficient. And from chat, wouldn't this possibly make a finished writer's broadcast hit a waiting reader first before a waiting reader if there are both waiting readers and writer, which means observed ordering priority of writers before readers? Yes, this will no longer guarantee the priority order between writers and readers. If you have only one condition variables, you are no longer going to be guaranteed this one necessary. And yeah, although it is still, you are not guaranteed the readers when you wake up, but still, if you want to proceed, the while loop will take care of that. So from the point of view of accessing the database, the while loop is going to enforce the priority because a reader, it's going to look whether there are active writers or waiting writers. And if there are waiting writers, it's not going to proceed, right? So as long as there are waiting writers, these while conditions will ensure that the reader cannot proceed. So actually the priority is still enforced, okay? So the priority is enforced by the while loop conditions. But the priority is not enforced in the sense that you can wake up a reader while you shouldn't have woken up. And this can lead, again, to deadlocks without changing the code and be more liberal in broadcasting the OK continue. Okay. Thank you. And I'll see you on Tuesday and Monday. Bye-bye.